Okay, so the next presentation should be given by the Prasenjit, Dr. Prasenjit, right? Related to the issues of wetlands in air pollution or the others. Okay, so Dr. Prasenjit, could you
Yes.
share your material right now?
Yes. Am I audible? Thanks for confirming. So I'm going to talk about a little bit of the sort of nature-based solutions of the raging issues that we are having in the Southeast Asia. Um, the part is that in this presentation, I will specifically focus on the vital role of wetlands in curbing the atmospheric pollution, focusing on PM 2.5. Now, it's a well-known fact that why PM matters. It's because of its detrimental health effect. It's about 6.7 million premature deaths has been reported due to the air pollution. In one of the leading journals in the US, Proceedings of National Academy of Sciences, they also report that 5.5 million premature deaths for indoor and outdoor air pollutions that has a connections with anthropogenic emissions. And about 3.6 million people have died because of the burning of fossil fuels. The estimated cost, which was estimated by the Clean Air Fund in 2020, was in 2015 it was 0.35 billion. That rose to 1.4 billion US dollar in 2019. So that's give us a sort of background that why we need to study more towards the towards monitoring this PM 2.5, because that has a lot of connections with the public funds and the public health safety. So these are some of the news reports that has been just collect some of the news reports published in UNICEF, Landsat, WHO, and one of the leading journals in India. They all says that the PM, particulate matter, is a vital factors for the premature deaths among the children and as old people. So we look into this top left image that suggests that the share of the deaths to the air pollution that was estimated from the GBD global burden of diseases, and we can see that in India, China, and some of the other countries in Southeast Asia has a very high share of deaths because of the air pollution. And if you just connect that pattern with the this animated images on the right side and at the bottom right and at the lower left side, you can see that there is a pattern. We have very high amount of pollution load in terms of the PM 2.5, in terms of carbon monoxide, in terms of nitrogen oxides, at least over the Southeast Station. There are a couple of other spots where we also have this high emission load. Obviously, for the carbon dioxide, US and Africa and Amazon basins have high load, but in terms of the PM 2.5, the Southeast Asian countries are having very high concentrations. Now, we're going to try to look into that basic idea that why wetlands are important. Now, if you look at the right side image, this is called the aerosol gun, which is a very normal image in National Capital Region of Delhi, where for a very high polluted days, in a very high pollution load, days with very high pollution load, has been treated in that way. So they use the water tank behind and that is inject the liquid water aerosols into the air, which can immediately arrest the floating suspended aerosols into the atmosphere and clean these areas. But in a way that these aerosol guns are not having a widespread effect. In other words, they have a very limited area effect. And it is also impossible to move several such aerosol gun in every part of these cities, for that matter. But what do we have? We have the same mechanism in our hand. If you look at the left side image, we have wetlands that can 24/7 that can supply moisture almost 24/7, and it acts as the same way that the aerosol gun is actually doing. So once it enters into the atmosphere, it just condensed on the surface of the aerosols, and then the condensation brings a lot of other water vapors into it, and gradually the size of the solid plus liquid assemblage is grown up, and ultimately they deposit into the surface. So the focus of the study is to find out the nature-based solutions to deal with PM2.5, and the objectives is to explore the effect of the wetlands, where here we are considering the joint effect of evaporation from the water surface, and I should consider the evapotranspiration, better way to say that, because it includes the soil moisture as well, plus the proximity of the wetlands in combinations with other meteorological variables to in combination with other meteorological factors to estimate the PM2.5. Okay, so to do that, to simulate that at a spatial scale, what we need is a set of meteorological factors: temperature at 2-meter height, relative humidity, wind speed, vertical airflow, the surface pressure, boundary layer height, and evaporations from the surface. Okay. We also need aerosol optical depth, which is sort of columnar aerosol load that includes everything, right? That includes total aerosol load. Okay. And I've also used it Sentinel-based, SAR-based image to detect the wetlands, and then we try to find out, based on the Euclidean distance method, we try to find out the proximity of the wetlands. And this is sort of X variables, and then we have Y variable, that is your ground observed PM2.5, which is sort of observed data from the Central Pollution Control Board. And because of their complexity of the distributions and the complexity of the relationship, they're not always having a sort of normal distribution. Therefore, we need to rely on something which is a data-driven method. And we, in this case, I use that random forest machine learning model with the training state of 70% of the data has been goes to the training state, and then to the 30% for the testing state. And we have done a sort of hyperparameter tuning using the random search cross validation method, and then finally we predicted at the 1 kilometer pixel resolutions. Okay, so we are basically this is joint work that's been done by many of our collaborators. So what we are basically targeting is that we are focusing on the major cities in the North Indian plain, sort of the part of the Indo-Gangetic plain. And this shows that the winter and post-monsoon have relatively higher PM2.5 load as compared to the monsoon and pre-monsoon, which is obvious that we have the wet scattering effect during the monsoon, and as the boundary layer height is pretty much higher in the pre-monsoon season, therefore there's a ventilation coefficient is higher, and that leads to a long transboundary transportation of those floating aerosols. So therefore, the pre-monsoon and monsoon has relatively lower PM2.5 load. On the right side, we are just using these what do you call, the box plot is just showing that the major controlling factor over the different locations, different cities, season-wise, we have a winter, pre-monsoon, monsoon, and post-monsoon. That's just the controlling factor, how they vary over the space across season. If we look into the correlation, which is obviously non-parametric because of the fact that the distributions are complicated, So we go for fetching the non-parametric relationship using Spearman correlation, and we found that the PM2.5 has a negative effect, a negative correlation with temperature, 2-meter height, the relative humidity, and wind speed, as well as boundary layer height, and it has a positive correlation, significantly positive correlation with EOD and evapotranspirations. Then if you just look into the simulated result from the random forest machine learning model, we observe that these modelers, the random forest regression model is quite efficient up to a level of about 150 microgram per meter cube. Because if you go beyond that, this suggests that the random forest regression model is somehow underperforming. There is the under predictions that you're anticipating from this model, but below 150 microgram per meter cube, it performs relatively better. The R-square value is obviously 0.6, 60% is variation is explained by that. But if you stop by taking the observations up to 150, this R-square certainly goes up to more than 0.75. And if you look into the influencing factor, which controlling factor has a higher influence, you can see that evaporations always have, evaporation has a very high influence. This DOI stands for the day of the year, which is sort of considering the time effect. The AOD, and look at the water proximity. This is something which we actually trying to find out. And this water proximity effect is even higher than relative humidity, wind speed, boundary layer height, and vertical airflow. And when we decompose them season-wise onto the right-hand side, we can see that there is a migration of the water proximity effect from winter to the monsoon. The important factor is that it's important to note that at the pre-monsoon season, this water proximity, which is otherwise for the whole model, it is below the EOD, but during the pre-monsoon season, which is the high thermal conditions, the water proximity has even higher influence than the AOD. And that's what we are actually concerned about. And with the winter and the post-monsoon, you can see that it is still having the higher effect as compared to the boundary layer height, vertical airflow, and relative humidity. So and look at the evaporation. The evaporation always have a very dominating influence. So in a nutshell, we can say that yes, the simulation results are actually suggesting that water proximity do have its control on curbing the PM2.5 load. So this is just the performance. This is just the performance of the predicted value, considering the test data sets, and for the cities, Kanpur, Agra, Lucknow, and Varanasi, Patna, and Kolkata, which shows almost a good approximation with respect to what the observations are. And once we are satisfied, we just apply that model spatially to model it at the 1 kilometer spatial resolutions, and that's what they look like. So I just made a GIF format, animation format, so that all of the cities can be seen season-wise at the same time. Okay. So when we do a transaction of the major water bodies of the wetlands, we can see that as we approaches to the water body, from this end to this is your water body, this is your water body. So the model, I mean, the estimated PM2.5 goes down, right? And that just happened for every situations, okay? And therefore, we take a buffer distance from the wetlands or the water body, considering it as 3 kilometer buffer distance and 9 kilometer buffer distance, and we take the mean of the estimated PM2.5 within 3 kilometer and mean of the PM2.5 within 9-kilometer ring, right? So 3 to 9-kilometer ring. And then we try to do a comparison between the mean of the PM2.5 within 3 km and mean of PM2.5 between 3 to 9 km. And we observe that almost all of the cases, in all of the cases for all of the season, the differences are significantly different, right? So that suggests that yes, water body has its effect. We call it as a limited area effect in reducing the PM load. Okay. So we published that paper back in 2022 over Delhi NCR, which suggests that as we approach to the main river touching the Delhi NCR, River Yamuna, the PM 2.5 load has significantly gone down, and that just happened for all of the locations controlling all of the monitoring stations. Okay. But you also look into the other part of the Delhi, where there is a canal, right, where the water usually flows on, and these the built-up area is tightly packed, right? So even if there is a water body, because of the emission is so high from both sides of this canal, the water body effect cannot be traced, and that just been seen in these graphics, okay, on the left-hand side graphics. So we therefore go for computing the fraction of water body in every grid cell of 1 km resolutions and try to find out, is there any connections between the fraction of water body and the PM 2.5 load? And we go for computing the entropy, which suggests that if you have a higher entropy value, that is PM 2.5 is very high. And then if I have a low entropy, PM 2.5 is low. And then we plot them together against we plot that entropy against the surface area fraction of the water body and see that, and we observe that if the fraction goes up, the entropy goes down. It suggests that if you increase the water body fractions in any area, that the PM 2.5 load is being significantly reduced. Okay, so the final notes that we get from this simulation result is that evaporation, aerosol optical depth, and surface pressure and temperature and NDPI are cumulatively explain more than 50% of the total variance. The variant influence factor shows that yes, the water proximity is the most important than wind speed, boundary layer height, in relative humidity. And the model also suggests that if you limit our simulations within 150, then the model performance will improve. However, if you go beyond 150, the model performance will come down. Perhaps some other sort of other factors are controlling it. Okay, we need to explore that. So water body has its proximity effect within 3 km. It reduces the PM 2.5 load pretty much well, but beyond 3 km, it is not so efficient. So therefore, we call for restorations of the medium and large site wetland as they supply a large amount of water vapor into the atmosphere to reduce the PM 2.5 load. And that's just a one strategy in place, which could be in place with the existing pollution abatement mechanism. And thank you. That's all from my end.
Okay. Thanks for your interesting presentation. So the audience can provide your question or your comment on the note, and then we may have the discussion after this section. Thanks again for the interesting presentation.